So what we need to do in order to check whether a schedule is serializable or not is, one of the things that we can do is look at precedence graphs. So if we have non-permutable actions, and we have a sequence of actions in a transaction, what we do is we define a partial order of transactions by constructing a precedence graph. I must have you being silent, because otherwise it makes it very hard for me to talk over you. So please concentrate. One more hour, then you can do what you like. Think about it. So what we have to construct is a precedence graph. So we have T1 precedes T2. If there are two non-permutable actions, A1 and A2, and A1 is executed by T1 before A2 is executed by T2. So our actions were the read and the writes, and we have non-permutable actions, which are the ones that could not be executed in a different order. So with that we can build our graph. So if we have a graph that shows us this, it means that A1 is executed in T1 before A2 is executed in T2. Now, as we construct the precedence graph, what we are going to look for is for cycles in the graph. If we have a cycle in the graph, then we have a problem in terms of that being a serializable schedule. So a precedence graph is a directed graph in which the set of vertices is the set of transactions. So every vertex in the graph is a transaction, T1, T2, T3. And then we have an arc between T1 or Ti and Tj if Tj reads the value of an item written by Ti, or if Tj writes a value into an item after it has been read by Ti, or if Tj writes a value into an item after it has been written by Ti. So then we have an arc between those two transactions. Now, as I said, a schedule is going to be serializable if the precedence graph is acyclic, i.e. there are no cycles in the graph. If we have cycles in the graph, then the schedule is non-serializable. So for example, here I have two transactions executing together, and I have transaction 1 begins with the begin transaction statement at the time T1, and it reads the balance of some item X. And then it's going to increment the value of X by 100, and then it's going to write the value of X. At that point, the second transaction begins. It's going to read the value of X, it's going to multiply the value of X by 1.1, and it's going to write the value of X. Then it's going to read the value of another item Y, it's going to multiply it by 1.1, and it's going to write it and then commit. But just about then, our first transaction is going to read the value of Y, and then it's going to subtract 100 from it, and then it's going to write to it. So here we have that transaction 2 is reading an item after it has been written by T1, and at the same time, transaction 1 is reading an item after it has been written by T2. So we have those arcs in the graph, and the arcs form a cycle. Because I have a cycle, it means this cannot be a serializable schedule. So I cannot execute this, interleave this, without having the same as a serial execution of the transaction. So this is not a serializable schedule, because when I do the precedence graph, I can find cycles in the graph. One way to cope with transactions in the concurrency mechanism is this idea of locking. And remember that I said that the scheduler was the lock manager. So when we're using locking, there are other mechanisms of concurrency, but locking is quite a often used mechanism, if we're using locking as a method of concurrency, then that's going to be managed by the scheduler. What happens is, what we do with locking is we try to manage as much concurrent execution as possible. And we have that permutable actions, which we say were actions on different granules, or read actions on the same granule, are compatible. But when we have non-permutable actions, we have to be aware of how we handle that in a concurrent system. So what we have to do for non-permutable actions is we have to have a locking mechanism. And what we do is we have two types of lock in the simplest form of locking. What we call a share lock or a read lock. So when a transaction has a share lock, other transactions might read the data, but they might not write it. Or I could have an exclusive lock, a write lock. And that means that other transactions do not have access to the data that is being locked by a particular transaction. And the locks are granted and released by the lock manager, the scheduler, who is managing the concurrent execution of the transactions. So it's going to manage this with some form of table structure where it keeps information on the locks. And that might look something like a lock table where I have a transaction ID, I have a granule ID, and the granule could be a tuple, could be a page, or could be a whole entire file. And I have a lock type, whether it is a read lock or a write lock. So I have to keep track of the locks that I have for the different granules associated with different transactions. So the lock manager is going to then, when a transaction operates, it needs to request the locks that it needs to perform its actions. So if the transaction is only going to read the data, it can request a share lock. If it's going to write the data, it needs then an exclusive lock. So now the transaction can access that data. And the lock manager is going to have to refuse incompatible locks. So incompatible requests. So let's say that I have a transaction 1 which has a share lock, a read lock, on an item, on a granule G1. If another transaction requests another share lock, that will be granted, because I have only a share lock, so the transactions can read the data that my transaction T1 is manipulating. So read are permutable, so these will be granted. Another share lock will be granted. If T1 holds a share lock and another transaction requests an exclusive lock, that will be refused, because you cannot read, write are not permutable, so I cannot grant an exclusive lock to the second transaction while the first transaction has a share lock on it. If T1 holds an exclusive lock on the granule, then every request on that particular granule is going to be denied, because an exclusive lock is going to automatically mean that we do not grant any other requests. So the transactions which are refused, they have to queue until they can get the necessary locks to execute. So transactions will be waiting to access the necessary locks so that they can continue execution. And we can guarantee maximum concurrency and execution that is correct if we use this locking system in conjunction with what is called the two-phase locking mechanism. Using locks alone, if we don't use them through these two-phase locking mechanism, might not guarantee the correct execution of transactions. But if we use this two-phase locking mechanism, then we can guarantee correct concurrent execution. So the idea of two-phase locking, which is the standard scheme used to maintain the level 3 consistency that we talked about earlier, the highest level of consistency, is that the locks are managed in such a way that there is a growing phase and then there is a shrinking phase. In the growing phase, a transaction has to acquire all of the locks that it requires for its operation, and it doesn't release any locks. In the shrinking phase, the transaction releases the locks, but it cannot acquire any new locks. So in this two-phase locking mechanism, first the transaction has to acquire all of the locks that it needs, And then once it starts releasing the locks in the shrinking phase, it cannot acquire any new locks. So if we use this two-phase locking mechanism, we can guarantee that concurrent operations execute correctly. And we can guarantee this phase 3 consistency level. We might still have problems, because what happens in this kind of systems is that sometimes we have a deadlock. Transaction 1 is waiting for a lock, which is held by transaction 2. And transaction 2 is somehow waiting for a lock that is held by transaction 1. So neither of them can proceed. So they are stuck there, each of them waiting for a lock that the other one has. So deadlock is a circular waiting condition, and it might not be straight, but there might be deadlock through more than 2 transactions. So we have some kind of circular waiting condition where one transaction waits for another, which might wait for another, which might wait for another, which waits for the first one. So again, that will be a form of deadlock. So there are a number of ways in which we can resolve deadlock. One of them will be trying to detect deadlock when it happens. So this might mean one of the possibilities is having a graph, a waits for graph. So I'm looking at transaction 1, and if it's waiting for another transaction, I draw a graph of that, and then another, we will see an example of this in a minute. So if I can draw this kind of a graph, where I'm looking at what transactions are waiting for other transactions, again, if I have a cycle in that, I have deadlock. So whenever I have a cycle in this waits for graph, I have deadlock and I have to break it. So in this waits for graph, I'm going to have it's a directed graph in which the nodes are transactions again, but in this case the arcs, the directed arcs, are when a transaction is waiting for another transaction. And generally, the deadlock frequency has been proposed as being rising as the square of the degree of multiprogramming and as the 4th power of transaction size. So the larger the transactions, the more multiprogramming I have in my system, the more likely that I am going to have deadlock. Because larger transactions might increase the amount of deadlock, so does multiprogramming. So we could have 3 schemes to detect the deadlock. We could not worry about detecting deadlock. So every time that I have a transaction that looks to be idle, I just abort it. I'm not trying to look at whether it's deadlock or not. If I see a transaction that hasn't executed for a long time, I abort it. This is cheap in terms of looking for deadlock, because I don't have to do it, but the transaction that I abort may not be in deadlock. In which case, it becomes expensive, because then I have to redo all of the operations that have been so far done by the transaction. So it's a bit simple, but it's indiscriminate. I could apply this every time a transaction is blocked. This again is going to be, you two have to be quiet, because you spend the whole entire lecture chit-chatting to one another. I know that sitting in the table might be the right thing to do, but you have to be quiet. Now you are slightly getting on my nerves. So don't make it worse. Every time a transaction is blocked, it becomes expensive, because, again, transactions might be blocked not because they are involved in deadlock, or optimally we will do it periodically. So occasionally we will look to see if there is deadlock. Shorter periods are, if we look for deadlock too often, we might look unnecessarily. If we look for deadlock over very long periods of time, we might not detect it early enough. So there's got to be an optimum period which has to be worked out by the DMS as to when we look for deadlock. And the graphs that have cycles in them, and which are the type of waits for graphs that might tell us there is deadlock, is something like that, where I have T1 is waiting for, T2 is waiting for T1, T1 is waiting for T2, and then T3 is waiting for T2. But I have a cycle there between T1 and T2, so there is a deadlock in there. Equally here, I have T2 waiting for T1, then T3 waiting for T2, etc. And again, I have a cycle there, so I have deadlock. So deadlock might be not just simply between two transactions, but more than two transactions might be waiting for one another, causing deadlock. And that has to be dealt with. So how do we resolve it if we have it? Well, normally what we have to do is we have to abort one of the transactions that is causing the deadlock to resolve it. Then the deadlock will be resolved and the other transaction can execute. So the simplest case is aborting one of the transactions and then restarting it. If one is waiting for the other, I then allow one to continue and then the other should continue afterwards. However, if a transaction is very large and it has involved a lot of changes, this could be expensive. To have to abort the transaction and do all of the changes, have to restart again. So generally it is good to abort the one which has done the least work. But estimating that might be difficult. But what I want to do generally is abort the transaction that has done the least amount of work. That one has to be restarted, but at least I haven't lost a lot of work of another transaction. However, if the victim, if the one that we abort is always the transaction which has done the least, it might be that the same transaction is repeatedly aborted and it never completes. And that is not going to be satisfactory. So I have to have a way of making sure that I always abort the same transaction, because if one transaction is done a little bit of work and then I decide it is the newest transaction, so I'll abort it, and then I start again, there's another deadlock, and I abort it again, then that transaction is never going to complete. So generally, it's good to abort the most recent transaction, because that is the one that is likely to have done the least amount of work if it has just started. But then what we do is we restart it with the original identifier, so it looks older. So if the first time it looks like to be the newest transaction, if we restart it with the original identifier, it will become older, and at some point it will have some chance of completing. So that is one possibility. If we have a transaction that is repeatedly aborted because it's the newest, but we started with the old identifier, eventually it will become the older transaction and it will be allowed to complete. So then we don't have a situation where the same transaction is aborted over and over again. Other things that we might do might be abort the transaction that minimizes the amount of work done, i.e. the changes that have been done to the database, or something more complex, like there are ways of solving this looking at things like minimal cut set of the graph, and then abort the corresponding transaction. So this could be an NP complete problem, so it's going to be much harder to compute. So generally, we go for a simple approach. So repeatedly, for example, restarting the youngest deadlock transaction until there are no deadlocks is practical, and it doesn't take us a lot to implement that. So it's a reasonable solution in terms of getting rid of the deadlock. Now, we've already looked at SQL for transactions, and we know that if we want to have a transaction, we want to take care of transactions, we have to have a start transaction or a start or begin. It changes from language to language. Sometimes more of one of these work. In PostgreSQL we can use begin. Probably works as well if you use a start transaction. And then we have a set of data manipulation language statements. And then we can have a commit, in which case all of the changes will be then committed and saved to the secondary storage. Or we could start the transaction, then find there is an error, there is a problem with the concurrent execution, there is deadlock, whatever, and we have to abort that transaction. So then all of the changes that the transaction would have had done until that point will be rolled back. And that means that we're back to where we started, which is again a consistent state. There are sometimes the possibility of having save points. So if the transaction is doing a lot of work and we want to break the point at which we roll back, if we roll back, we can have a start transaction, we can have a save point, and at that point there will be a partial kind of like saving of the results. Then we have more SQL statements. What we can then do is roll back to the save point instead of to the beginning. So if we have transactions that are very long and very complex, it might be worth having save points, so when we roll back, we don't roll back to the beginning, we might roll back to the closest save point. That is where you have complex transactions. And then you could have a number of save points, and you can roll back to whatever save point you choose. So, if I had it in pseudo SQL, I will have something like begin or begin transaction. Then I will have select balance as a balance from current account, where the account name is Joe. Select salary from experts, where employee name is Joe. Update the current account, set the balance equal to the old balance plus the salary, and commit. All of that has now become one transaction. So it's either going to completely execute, or none of it will be executing. And the other one might be a different transaction where I, again, begin transaction, and I am going to, instead of add the salary, I'm going to subtract the phone bill, then that will all be packaged as one transaction, so it will commit, and they can execute concurrently. Now, we've looked at concurrency, we've looked at the transaction mechanisms, we've looked at the problem with deadlock. So the next thing that we need to understand is this concept of the recovery mechanism. So how do we get this consistent database in the presence of failures, which could be system failures, network failures, fires, etc. The DBMS needs to execute transactions reliably to deal with failures, and the failures may be caused by human error, they might be caused by a programming error, they might be caused by a problem in the environment, fire, whatever, a network failure, a hardware failure. So there can be all sorts of failures that the DBMS has to cope with. But it always has to have a consistent database. So that is the job of the recovery manager. The recovery manager must handle all of the problems associated with failure. So how is he going to do that? You have things like transaction failures. So I have two failures, they are in deadlock, one of them gets aborted. So that is a failure. The transaction has to be restarted. Or I have a system failure. I'm operating, the power goes off, the computer goes down, and whatever I was doing at that point disappears because it wasn't safe. It was just in main memory, so it has to recover from that. The contents of my memory will be lost, and I would have lost the work that I was doing. Or we could have media failures. The disk is damaged, the head of the disk is damaged, whatever. Or I could have a communication failure in the network. So a message is lost, and it doesn't reach the destination. In any case, the DBMS has to sort all of those failures. And when we look at the amount of failures that occur in the system, the majority of them are disk failures, followed by power supply, the network, then processor, and then memory failures. So, and that's supposing that all of the failures are independent of one another. But obviously we're going to have to deal with a number of different failures at different rates. So what we need is, we need to be able to reconstruct a consistent state whenever there is a failure. We need to be able to go back to a consistent state. So we need to reconstruct the database history. And that means that the DBMS must maintain some history of the database as it operates, in able to be able to recover the operation. And we need to be able to recover things like the logical entities, so the tuples, the attributes, values, etc., the physical entities, so the pages that are being transferred to and from main memory, the state changes, an old value versus a new value, and the operations, the transactions that are occurring with their parameters of the transactions. So the systems generally have a log which records pages, the physical entities. So it records a before image, before an operation image, and an after operation image. That way it can roll back to what happened before a particular operation started, or it can go back to the image after the operation started. So the log files are going to be the mechanism for keeping all of the updates of the database as they happen, so that we can recover in the event of failure. And that is going to have several types of entries. We're going to have the before image and the after image. So that is going to be the page value before an update with the transaction identifier that is related to that particular update, and the after image with the page value after any update with the transaction identifier. We might also have to record a begin transaction record. So that is going to give us information on when the transaction starts, the transaction identifier, and the timestamp that tells us the time at which it started. You might also have to record the commit record for when a transaction commits. So we know it has been committed. So that is going to then tell us, if there is a commit log, that the transaction has been committed and all of the updates have been made to the secondary storage. So that should be a committed transaction. Then we know that the updates have been transferred to secondary storage. We also need to maintain the abort records. So if there is a problem and it rolls back, we need to log that so we know that the transaction was aborted, and therefore we have to go back to before the transaction started to execute. And we have to assume that the log never fails, because if the log information goes and we have no access to it, then we couldn't do any of the recovery. And that means that the log must be maybe kept multiple times, not just one copy of the log, but there might be different copies of the log kept at different locations, so that we always have access to the log information in the event of a failure. So, how do we guarantee the safety of all of the data in the database? One of the things that we need to do is to take a backup periodically of all of the data and the states in the database. We need that because if there is a major loss of the information stored in secondary storage, then we recover from the backup. So, for example, the university takes a backup of my laptop, supposedly. So if my laptop was completely, the disk completely failed, I will go to my backup and then I will have the information restored to my computer. So similarly, in a database, there are events in which all of the information will be lost, and we need to have a backup to restart the system. And that backup needs to be done when the database is in a consistent state, because we want to record the consistent state of the database. Generally, that might be copied onto tape, because tape is quite a cheap method, and we might not need to access it that fast, so that's fine. And we're going to use that when we have a media failure. Then we will go on to the backup, and we'll restore from the backup. Often, when we're talking about backups, they have to be stored on site. So if there is a fire, for example, if you have a fire, and the backup is kept in the same place as the system, then it's not a very good backup, because it's not going to be helpful to you, because it will go as well. So generally speaking, the backup is kept somewhere else. What we might have as well to help us is checkpoints. And checkpoints are the final point of synchronization, where everything that is in the buffers gets saved to secondary storage. So at the checkpoint, all of the pages that are still not committed are written to secondary storage. And that allows us to know that if we reach the checkpoint, as we will see in a minute, then we can assume that certain things have been committed. So that might be used to restart after a system failure. We can go back to the last checkpoint, see what was committed at that point, and then either undo or redo the transactions that were happening at the time of the checkpoint. So that is going to shorten the recovery time if we have checkpoints, because we don't have to process so much of the log. We don't have to go to the last backup, we just go to the last checkpoint, which is the last point at which we know things were forcibly written to secondary storage. And we know that the database then should be in a consistent state. So, how do we ensure that we have a reliable system at all times? If we have a page update, we write them first in the memory buffers, but if the system fails, that is lost, because that is not permanent. So the modified pages that are in the buffers are called the dirty pages because they haven't yet been written to secondary storage. They're just in the buffers. So to guarantee a transaction atomicity, we need two rules. The first one is the commit rule that says that all dirty pages must be copied to the stable storage before the transaction commits. So if the transaction has made some changes, and those changes are in the buffers, but they haven't committed to secondary storage, before we commit, we must guarantee that the changes are written to secondary storage. Then we can commit. Then we are certain that the transaction has finished its work and is committed to secondary storage. And the other thing is the log ahead rule, where if a page has been modified before the end of the transaction, then the before image must be logged so that we can look at the before image in the event of a failure. So if the transaction needs to be undone, we can look at the before image to return to that point before the transaction started. So then, the type of recovery that we're going to have is going to depend on the type of failure that we have. If we have a normal recovery, we restart after a normal system termination, then we just have to recover the execution state of the problem. So we can look at the log and look at the last point of execution, and we just start from there. If we have a system failure, then we have what we call a warm recovery. We will assume that all of the updates by committed transactions have been preserved in the storage, but all of the transactions that were proceeding at the time of the failure, we need to either redo or undo, depending on what happened. And a cold recovery, which we have if we have a media failure, means we have to go to the backup. So if we have a cold recovery, we have to first of all restore the database from the backup. Once we have done that, then we can look at what was the state when there was the failure, and then try to restore if necessary. And we also have to think about, well, the DBMS has to think about how to cope with a failure when it is trying to restore. So you have to cope with failure in the event of a failure. So what happens if your backup recovery procedure fails? So it has to also think about how to cope with further failures that occur when we're trying to recover. And it has to have alternatives for all of that. And all of the procedures must work and be error-free. So it has to guarantee a lot of things. So if we have a system failure, and I'm thinking about whether I have to redo or undo particular transactions, and I have a system with a checkpoint, where the checkpoint tells me anything that happened at that point would have been forcefully committed. Anything that would have been committed would have been then stored into secondary storage. So I have to look at different types of transactions. Those that committed before the last checkpoint. Thus, we assume that if they committed before the last checkpoint, they would have been made, the changes would have been made to secondary storage. So those we consider to be done and committed. Then we have those that started but were not committed at the last checkpoint. So they were still proceeding at the last checkpoint. But they might have committed before the system failure. So they committed before the system failure, but not before the last checkpoint. So what do I do with those? Then I have those that started before the last checkpoint and were still in progress when the system failed. And then I have those that started after the last checkpoint and committed before the failure. And then finally I have those that started after the last checkpoint and are in progress when the system failed. And I got to decide for each of those whether they need to be undone or redone. Okay? So the way to do that is as follows. If I have something like that, I look at my checkpoint, which is this, and a time of failure. And I have various transactions at different types of execution. The first one, T1, started before the checkpoint and committed before the checkpoint. So that one should be stored in secondary storage, and that is a finished transaction. The second one started before the checkpoint but it hadn't committed at the time of the checkpoint, but it did commit before the system failure. The third one started before the checkpoint, but was still ongoing when I had the system failure. The fourth one started after the checkpoint, but committed before the system failure. And then the final one started after the checkpoint, but was still ongoing when I had the system failure. So those are all the type of transactions that I have. So what I have to do if I have a recovery in this situation is I have an undo list and a redo list. Undo list is the list of transactions that I'm going to have to roll back to the beginning to get into a consistent state. The redo list is the list of transactions I am going to have to redo all the way to the committed point to be in a stable stage. So if I look at that, at the beginning I have my undo list and my redo list, and they're both empty. Then I read the log back to the last checkpoint. So I read the log back to this checkpoint. And I know there that the transactions that are active, they either have to be in the undo list or the redo list. So in this case, my active transactions were T2 and T3. So those two transactions were active but not committed, so I have to put them in the undo list, because they didn't commit at that point. So I need to, from that point of view of the checkpoint, I might need to undo the work that was done, because it didn't commit. Then, once I've done that, I read the log forwards, and I remove any transactions from the redo list that had actually already committed. So I look at the undo list, and then put in the redo list if I find a committed statement. So for example, in 2, I had it as something that I should undo, but when I look forward, I realize it had committed before system failure, so I can redo that transaction. So I put it in my redo list. The same cannot be said for T3. I cannot put it in my redo list because at the time of system failure, it had it committed. So I had to undo the transaction to the beginning. So I keep going like that. So I end up then with my transactions. Then at the end of that, the undo list is going to have T3 and T5, and the redo list is going to have T2 and T4. So T2 and T4 I can redo because I found the committed, that the transaction committed before the system failure, but T5, which was still going, and T3 I had to undo because they hadn't committed at the time of system failure. So, having got my list, then I look at my after images and my before images, and I use the before images to undo the updates on the undo list, and I use my after images, which I would have from the committed record, to redo the updates of transactions that are on the redo list. And then I am back to a consistent state in the database. So that is what I have to do.